Hello and welcome guys. Welcome to the machine learning series tutorial. So in this video we will be doing one project that is related to car price prediction. Okay, so the problem statement is, so there is suppose a Chinese automobile company ABC aspire to enter the US market by setting up their manufacturing unit, in that location only, and producing car locally to give competition to the existing US and European countries, counterparts. So the goal will be of this business that we will be required to model the price of car with the available independent variables. So it will be used by management to understand how actually or exactly the price vary with the independent variables. So they can accordingly manipulate the design of the car, the business strategy, etc., to meet the certain price level. Further, the model will be good way for management to understand the price dynamics of new market. So we have two files. One is the data dictionary, in which you will be able to see the name of all the variables as well as definition of the variable. Okay, and the second file is the data set that we will be using for this project. Okay, so here we have all the features, and to understand all this feature, during the project I will explain each of them, whichever we are using for modeling part. But if you still want to understand it before the project, you can just refer the data dictionary. Okay, so now let's go to the project part. Okay, so here we have a folder of car price prediction assignment. Now let's create a Python notebook file. Okay, so now again what we do first, we first load the data, and before that we load all the libraries that we will be using for this project. So let's do that first, and we will be understanding data. We will be covering all the stages of machine learning architecture. Here we will be doing EDA also to understand the data deeply, to be able to explain what actually is happening inside the data. Okay, so let's do it. Okay, so the solution part will be divided into 4 section. Okay, let's define the solution part. Majorly 5 part. Then we will be doing data exploration, data cleaning if required, but I think it will be required. Then data preparation, as well as feature engineering. Okay, and last will be model building and as well as evaluation. Okay, so our solution part will contain all these stages. Okay, so let's convert into markdown. Okay, yeah, so now what we can do is let's import all the libraries that is needed for this project. So okay, as usual, numpy, pandas, matplotlib will be there. Okay, okay, we'll see the model part later. Inserting the library for all the models, we'll see that part later. So now we can also import Seaborn here, since we will be doing some EDA as well, and for EDA Seaborn is a very best library. Okay, so we imported all the required libraries. Now also import warning here, because some of the library may have deprecated, and for that we may see warning. So for ignoring those warning, there is a library called warning, and it will help us ignore all those warning that we will be seeing during the coding part. Okay, so let's ignore all those filter warnings. Okay, just ignore. Okay, now let's read the data. Okay, so let's name it cars pd.read csv, and here we will import our car price assignment csv file. Now let's look at the first few rows, how they look like. We already have looked in the excel file as well, but let's see here as well. So we can see that we have 26 columns as well as 5 rows. So this is how it looks. We have symboling, car name, fuel type, whether it is gas, petrol, diesel, etc., aspiration, door number, how many door are there, driver wheel, wheelbase, engine size, some of the feature already explanatory. Then the price. Okay, then what is a mega per highway mpg, and then compression ratio, stroke, fuel, engine size, all of those. Okay, so let's see the info, what is the data types, as well as do we have null value or not, and how we do that using dot info. Okay, so cars dot info. Okay, so here is the information about the data set. So we have these many features. We have around 205 entries. Okay, and you can check that with dot shape also. Data frame dot shape will give you the size of the data set, that is 205 rows and 26 columns. So I mean, we can see that we have not much data, but this is what we have. Okay, now you can see all the data types. It have some categorical data as well, integer, float, all of those. Okay, now let's understand the some of the feature that is we will be using for our modeling part. Okay, so I mean, the data dictionary contain the meaning of all various attributes. Some non-obvious ones are, for example, let's take symboling. Okay, the second feature after the car ID. So cars of symboling. Okay, let's first check what is the data type. Symboling is a int64. Okay, and what does it contain? Symboling. Okay, let's check all the unique values. Okay, it has 1 2 0 3 -1 -2. So it's like values between -2 and +3. Let's understand if there is any definition written for this symboling. So it says it has assigned, okay, insurance risk rank. Okay, so this is like a rank for insurance, and -2 will be least risky, and +3 will be most risky. Okay, and most car have values between 0 and 2. That is what I have googled it and understood. So let's see how many for each of the category, how many rows we have for each of the category. Okay, so let's do value count. Okay, and before that we need to do as type category dot values count. Okay, so we can see that for most of the cars, like for value of 0 and 2 and 1, it has values more than the other ones, the risky ones. So 0 has 67, which is the max, and -2 has least, that is 3, and that is what we have got from this symboling feature. Now let's understand another feature, that is fuel type. We know car name is not needed. Aspiration, let's understand aspiration. Okay, how aspiration look like? Okay, it's like a categorical data. So let's check the unique first. Okay, and let's copy the name, and we can see it has two values, that is STD and turbo. Okay, so let's understand what is this. So aspiration used in a car. Okay, so it's type of feature that is used in a car. Okay, so it's like a internal combustion. So you can say an engine property showing whether the oxygen intake is standard through atmospheric pressure, or though turbocharging. So that is pressurized oxygen intake. Okay, so let's see how many car of them are standard atmospheric pressure, as well as how many of them have turbocharging oxygen intake. So for that, again we'll do value count to understand the variability in the data set. So cars of aspiration, category, and value count. So most of the car we see that have standard atmospheric pressure, that is basically showing whether the oxygen intake is standard or turbocharging. Okay, so we can see that 70% of data, more than 70% or around 70% of data we see that it has a standard oxygen intake. Okay, now another feature is driver wheel. Okay, door number we self explanatory. Car body is also self explanatory, whether it is a sedan, hatchback, convertible. So let's see how many different type of car body we have. Okay, for that again let's do value count of car body, and we'll get to know that most of the cars are sedan and hatchback, and remaining are wagon, hardtop, convertible is very least, that is 6, number of 6. Okay, now let's understand driver wheel. Okay, so for that also let's do value count. Okay, driver wheel. Okay, it's saying some error. Oh. Okay, I might have wrote. Okay, yeah, drive wheel. Okay, so we can see that drive wheel have front wheel, rear wheel, and four wheel drive, and we can see that for FWD, that is front wheel, having 120 rows, and for rear wheel we have around 76 row, and four wheel drive we have around 76, oh no, sorry, 9. So that is what drive wheel is, and so basically it is saying type of drive wheel. Okay, yeah, so now let's plot this drive wheel. Okay, so what is the distance between center of front and rear wheel, that we will be get to know. Okay, so for that let's do SNS plot, which is seaborne plot, SNS dot distribution plot of cars, and let's say for wheelbase. Okay, so wheelbase is wheelbase of the car. So we'll get to know what is the size of wheelbase. Okay, so let's run this, and we can see the distance between center of front and rear wheel. This is how distance are. Okay, so if we categorize, if you include the categorical data of forward, then rear wheel and the four wheel drive, you will get to know that for for forward and 4WD, the wheelbase is almost close to each other, but not every time. And for RWD, which is rear wheel, it will be bigger. Okay, so the peak that you see is for this rear wheel. Okay, so how to find out that? So let's write a one line code. So let's copy this code, not this. Okay, and what we need to see is FWD. Okay, and we want to check feature this dot mean. So basically what this line of code is saying is that, so I am checking whether what is the mean of wheelbase where drive wheel is front wheel. Okay, and same way we can do for RWD and 4WD. Okay, so let's run each of them. So you can see that for forward and the four wheel drive almost similar, but the rear wheel is like the peakest. Okay, so this one, so that is what we have understood. Okay, now next thing we will be exploring is that, let's check our feature set. Wheelbase is done. Okay, let's understand, car length, width, height doesn't matter actually, because they are not need to be analyzed. Okay, so we can distinguish car with their car body, so like sedan, hatchback, all those things. So let's ignore for those for now. Let's understand curb weight. Okay, so this is a weight basically of car without occupant, or you can say baggage. Okay, so let's see what definition says. The car, okay, the weight of car without document. Okay, it's the same thing. Okay, so let's understand this data as well. So let's create some space. Okay, so again, so we will be doing distribution plot. So let's copy this line of code, and here we will pass our curb weight. Okay, now let's run it, and we can see that the most of the dense region, that is in between 17 to 1800, and up till 30 3300 something like. So 1700 to 3300 is the dense range where most of the uh, weight of the car lies, and you can see the peakest value is around 2400. So this is what we can interpret with this feature. Now let's see another feature, that is engine type. Let's see how many different engine type is there in our data set. So let's again copy the value count code. Okay, oops, should be here. Okay, so we can see that there are different type of engine type, that is OHC, with the highest number of engine types. So OHC is like a type of piston engine where the camshaft is located in the cylinder head, so above the combustion chamber. So this is the most common engine found in the cars. So its full form is overhead camshaft. Okay, and that's why we can see that, I mean, most of the car carrying OHC type of engine type, and least popular is DOHCV. What does that mean? So it's like an enhanced version of all this. So basically this stands for dual overhead camshaft. Okay, so this type of engine have two camshaft per cylinder bank, in which one camshaft control valve that work as a entrance for mixture of petrol and air into the combustion chamber. Okay, so there is one separate camshaft for intake and exhaust valve, and I mean that is why these type of engine can have higher performance than other general engines, that is OHC or OHCF, all those other engines. Okay, so let's understand another feature now. Okay, so cylinder number not necessarily important. Engine size now. Okay, let's understand stroke. Okay, so what is stroke? So stroke is the some value. Let's see what stroke says. So it says volume inside the engine. Okay, stroke or the volume inside the engine. Okay, so let's see the distribution plot, and we will be able to understand where most of the value lies. Okay, so we can see that around 3, in between 3 and 3.5, most of the value lies, and this is like a volume of engine, or you can say the distance traveled by the piston in each cycle. That is what stroke means, and we can see most of them having 3 to 3.5. Okay, so it's like a distance traveled by the piston in the each cycle, okay, inside the engine. So that is what I mean this says. Now let's say another feature, stroke. Okay, compression ratio is important feature, so let's understand compression feature also. Just copy this line. Compression ratio. Okay, so basically this compression ratio says ratio of a ratio of volume of compression chamber at largest capacity to least capacity. Okay, that is what compression ratio says. I mean, just understand that this ratio is very important for car. Why? I mean, because the compression ratio is a ratio of volume of the cylinder when the piston is in bottom position, that is B bottom, and the and in the top position, which is V bottom. So the higher the compression ratio, greater the power output for that engine, and that is why it is important. Sorry, it will give greater power output for the engine. So that is why it is important, and it is calculated by the ratio of by dividing the piston before compression and after compression. So this is how it get calculated. So let's see how our distribution look like, and we can see that most of the compression ratio value lies between 7 to 10. Okay, and then for more detail you can go through some Google articles. Okay, let's see our another feature, that is, okay, let's see overall how horsepower is distributed. Okay, okay, we can see most of the horsepower is lying between 50 to 200 range, and horsepower, everybody knows, it's like a power to the car. So it's type of metric that is used to indicate the power produced by car engine. So that is what it says. Now peak not needed, CTMPG. Okay, let's see our target variable, that is price. Okay, so let's see our price distribution plot. Okay, so we can see that most of our car valued in between between 7,000 to 25,000, and we have few more variability in between 25,000 to 45,000. This is because these are expensive cars, and these are like a as usual rate, that is 7,000 till 20,000. Okay, now let's move to data exploration part. Now to perform linear regression, the numerical target variable should be linearly related, at least one another numerical variable. So let's see whether that's true in the case. And so we will first subset the list of all independent numerical variable, and then we'll make a pairwise plot. Okay, so first of all, let's do data exploration. Okay, now we'll take all the numerical features. Okay, so cars numeric equal to cars dot select d types. Okay, and here we will include only float 64 as well as int 64. Okay, this will make sure that we are only having numerical features. Okay, so let's see our all the numeric features, first 5 rows. Okay, and we can see all the numeric feature we have included. Now now here you might notice that car ID isn't of any use to build linear regression models, so let's drop that car ID. Okay, because this is type of feature that will more make any sense. Okay, so cars numeric equal to cars numeric dot drop car ID. Okay, and axis should be column, that is 1. Okay, so dot head. It's running saying car ID didn't found. Okay, it's in capital letter. Okay, so we have dropped our car ID features. Now now make a pairwise scatter plot and observe linear relationship. So to plot pairwise scatter plot, first we need to set figure size equal to, let's say, 20,10. Okay, now seaborne pair plot, and we'll pass our car features and then plt.show. So it will take some time to plot. So let's wait for some time. So this pair plot feature is very useful when we have a lot of features. So this will help us see the linear relationship between all the features. Okay, so it will be like heat map. So in the previous videos also we have seen how heat map look like. So heat map, what it does, it shows the correlation value but in the pair plot it will show the scatter plot distribution. So we will able to understand whether they are you know having linear relationship in between them or not. Okay, so yeah, now you can see that we have beautiful scatter plot. Now it's very hard to interpret currently, so you can see this particular this one, a few of them having linear relationship, but not most of it. So it's really hard to interpret when we have a lot of features. So what we can do is we can rather plot correlation between variables. Also a heat map is pretty useful to visualize multiple correlation in one plot. So let's do that. So correlation plot, so car equal to cars numeric dot core. Okay, now let's see. So you can see that for each of the features we have correlation variable. Now again, it's very hard for us to interpret all this value because they are numbers and our eye are very catchy to plots, right? So let's plot heat map instead of this so that it will be clearly visible. Okay, so let's do that. So plt dot figure, here we'll pass fixed size equal to 16,8 heat map, and here we will pass our correlation that we have found here. Now we need to set our C map also, so let's use the very common C map. Okay, yellow, green and blue. Okay, now we need annotation, so for that we need to set annote equal to true. Okay, plt dot show. Okay, now you can see beautiful plot, and hence we will be able to clearly explain what actually happening. So the correlation of price with independent variable. Okay, so the price you can see here with independent variable, so like wheelbase. Okay, so price is highly positive correlated with wheelbase. Okay, then car length. Okay, then car width also. So most of this feature you can see 87%, 84% not car height. Then we have horsepower. So notice how all these variable represent the size, weight, engine power of the car. Okay, so you can see that these are approximately highly correlated with price. That is what we wanted to include in our modeling part. Then we have, you can see, negative correlation with city MPG. Okay, then highway MPG, it's approximately like -70%, and this suggests that car having high mileage may fall in the economy car category, and they are priced lower, like for example Maruti Alto, Swift type of car, which are designed to be affordable by the middle class who value mileage more than horsepower or size of the car. So correlation among independent variable, many variable are highly correlated. Okay, so like wheelbase, car length, cube weight, engine size, etc. So these are all measured of size or weight, and they are positively correlated as expected. So thus while building the model we will have to pay attention to multicollinearity. Okay, so we'll see that later part. Now let's move to the cleaning. Okay, data cleaning part. Okay, let's see whether we have missing value or not in the data set, and we will also seen that the variable are most of them were correct in the format. Okay, so let's see the variable format again. So cars.info, so it will show us all the data types. So what we need to do next is we need to extract the company name from the column called car name. Okay, so car name, let's basically see what first few entries look like. For that, let's do this, car equal to car names. Okay, car name, and what we want to see, let's first 20 entries. Okay, it says car name. Okay, so we can see that these all are first 20 car names. So notice that car name in which there have some gaps, spaces for Alpha Romeo, Audi. Okay, Audi, Chevrolet. Okay, so these are, thus we need to simplify or extract the string before a space. Let's see how to do that to basically to bring out the brand name. Okay, this is what also called as feature extraction. So let's use split method to basically extract the car names. So for that, what we need to do is car names equal to cars of dot apply lambda x, and we will apply x dot split. Where split? In the space. Okay, and what we need the first value, so 0 will represent the first value. And now again let's see car names of first 20 rows. So now you can see we are easily able to bring the brand name instead of those spaces, dash, all of those things. Okay, now what we can do is I mean we can also use regular expression. So basically this method will help us bring the car name in another way. Okay, so let me show that as well. So it will be maybe useful for you also. For that, what we need to do is we need to import a library called regex. So we need to define first what we are looking for. Okay, so this is the second method. One method is using split, another method is using regex. Okay, so regex dot compile read w plus minus and question mark slash w plus. Okay, now this will help us bring the all the required names before the first space. Okay, what we are missing here? Okay, yeah, so now car names equal to cars of car name. Again we'll apply lambda x re dot find all. So find all will do look for all the spaces, and we are passing here the expression, and x is like a row value. Okay, and what we need first output. Okay, now let's print the car names. Now you will see same output we are getting, the very first before the space, very first characteristics before the space. So this is what will this will bring us all the brand name. Now let's create a new column to store the company name and check whether it look okay or not. Okay, so cars of car company. Okay, cars of car name dot apply lambda xre dot find all. P comma x, and we need the first output. Okay, car is not defined. Okay, so this is done. Now let's look at all the values, since this column will be used as a categorical variable. So cars, car company dot s type category dot value count. Okay, so now you can see that most of the car belongs to brand called Toyota, then Nissan, Mazda, Honda, BMW, Nissan again. So we have noticed that some of the car company names are misspelled, like VW is like nothing but Volkswagen, then it should be a Volkswagen. Then we have Porsche, which is again wrong name, then Porsche. So you can see, right, I mean Nissan with capital N, then Nissan with small n. Okay, so this need to be fixed, and this is what data cleaning or data quality look like, and this is how we look at actually. So let's solve this issue. Okay, so how to solve this? We will be replacing the misspelled car company names. Okay, okay, so for Volkswagen first, car dot location. Okay, so what we are looking for, we are looking for car of car company equal to VW and sorry or cars of car company equal to Volkswagen, that is this one. Okay, and in which column we want to fix it, with the same feature, okay, with the same name, that is car company, where I want to fix the value. And what it should be Volkswagen, where I mean that is the correct name of the car. Okay, so now let's fix other car, that is Porsche. Okay, same way, I mean just copy this line, car company should be PORCSHCE, right? Yeah. Okay, now it need to be fixed in the car company feature, and it should be PORSCHE. Okay. Same for Toyota, Nissan and Mazda. Let's do for all those three. Okay, so it will be Toyota, so it is Toyota. Okay, yeah. Then it will be Nissan. Okay, so it's in capital letter. Then we have Mazda. Okay, so we have replaced all the misspelled car names. Now let's run it. It's saying in Porsche. Okay, there is a comma missing. Okay, okay, so we have replaced those. Now let's see it again. I mean the value counts. Okay, and it will increase. Now you won't see all those error that we were seeing. Okay, now Nissan has been increased to 18, whereas it was 17 earlier because of this capital Nissan. Okay, so hopefully we have fixed all the related issue. Now the car company variable looks okay. So now let's drop the car name variable, which is not required since we have I mean this feature. So cars equal to cars dot drop, and what we want to drop, card name. This is equal to 1, and let's see cars dot info, and we shouldn't have car name feature. Okay, so yeah, we do not have car name feature. Now let's check any for any outlier. Is there any outlier, and how do we check that? With the help of describe. Okay, so cars dot describe will tell us whether do we have any outlier or not. Okay, so what you can do, you can check standard deviation, min max, and 50% of quantile. So in most of the cases, I mean I don't think there is any outlier because the range is almost similar. Okay, somewhat it has in price, but it won't matter because some cars are already they can be expensive, and because of that we can see that standard deviation is around, okay, not this, yeah, standard deviation is around 8,000, and the maximum value is around 45,000. So in that case we cannot say that this is an outlier. So let's move to data preparation part. So now here we will prepare the data to build the model. So what we will do, we'll take a look at the data set again. So first of all, let's name data preparation. Okay, cars.head. So we have, you can see, I mean, not all features are visible, some of them are hidden. So to fix this issue, what we have to do is we need to use pandas set option function, where we can maximize the column and rows to be visible. So for that, what we need to do is pd.set option. Okay, and here we need to set display dot max rows. Okay, and here it should be none. Okay, now same for columns, set option max columns. Okay, so it is saying pandas has no attribute options. Okay, it should be not with s. Yeah, now you can see it ran successfully, and we can now see all of the features as well as rows also if we just directly print without head. So now you can notice that the feature name, door number, as well as cylinder number are numeric type with the number written as word. So let's map these to actual number to avoid too many dummy variable creation ahead, because again we need to make use of encoding to feed the feature as numerical, not as a string, because model will throw error if we don't feed the feature as a number. Okay, so let's create that. Also you need to note that you can also treat them as a categorical variable. These two are also symboling. Okay, and create dummy variable for them. It's up to you. Okay, so let's first of all do for cylinder number. So cars cylinder number. Okay, dot s type category, and let's see the different level of cylinder number. Okay, so we can see 4 6 5 8 2 12 3. Now let's check different level of door number. Okay, it has 2 and 4 only. So we'll create a function to map the categorical level to actual number, and you can see the categorical level above, and then use them for mapping, and that is what we will define here. Okay, so we'll create a function def number mapping. Okay, and here we will pass x. Okay, so return x dot map. So here we'll create a dictionary in which we'll define what to map for 1, what to map for 2, 3, 8, all those. Okay, now for 2 we'll map 2. Now for 3 we'll map 3. Eight, then we have 12 also. Okay, now let's run it. Now let's map to these two columns. Okay, so cars cars door number and and we will have cylinder number equal to cars of these two feature again dot apply num map. Okay, so if we run this, and if we run this line of code again, you will see that they have been mapped to numbers. Okay, yes, you can see they have been mapped to numbers. Now what we need to do is we need to create dummy variable for all the categorical variable. To do so let's subset all the dummy variable for categorical variable first. Okay, now let's see all this feature. Cover to no, head. Okay, so we have only few of them. So now we'll convert these to dummies. And how we do it? So for that, cars dummies equal to pd.getDummies. So pandas already have that feature. Cars categorical. Okay, now we need to, if you want to drop so when we make it to dummies, what will happen is, suppose drive will column has only two features, that is f I mean say it has rwd and fwd. So for rwd it will make 0, and for fwd it will drop it, and that is what drop first means actually. Okay, so let's drop them, and now let's see the car dummies first few rows. So you can see now for what we were looking, yeah, this one, drive wheel. Okay, so drive wheel fwd is there, rwd is there, but 4wd is not there, which means that it has dropped it, and that is what drop first means. So if the unique value is 4, the total number of column will be created as 3. If the unique number is 1, then it will have only 1. Then if the unique number is 2, the number of column will be created as 1, and this is how dummies works. So now drop the categorical variable column. Okay, so cars equal to cars dot drop list car categorical dot columns comma axis equal to 1. Okay, now what we need to do is we need to concatenate this as well as numerical ones, where this particular features. So let's concatenate both of them. Okay, we have already dropped, so that's why key error is. Okay, so now concatenate dummy variable with x. Okay, so the cars will be pd.concat cars comma car dummies, and axis should be column, so that's why 1. Now let's check the head again. Okay, so cars dot head, and we'll see all our categorical feature as well as the numerical feature we have added. Now you can notice that we have car id in this data frame. So let's drop that car id feature again. So cars dot drop car id. Okay, axis should be 1, and if you don't want to create a new variable, you can do in place equal to true, so it will make sure it deletes without assigning a new variable. Okay, so let's drop it. Now let's move to the model building and evaluation part. Okay, so from here we will start the model building part. Okay, so for that what we need to do is we need to import train test split, right, for splitting the data set. So let's do that. Split the data set, and for that let's import the required library. So from Scikit-learn dot cross validation, okay, cross validation not coming. Okay, import train test split. Okay, so I think for cross validation is outdated, so there is another way for importing it. So that is just remove cross validation with model selection, and we can import train test split. So now we need to split our data set into train and test. So for that, let's df train comma df test, and then we'll call our train test split function, and here we'll pass our whole data frame, and we'll define our train size to be 70%, okay, 0.7, and our test size will be 0.3, which is 30%, and let's set random state 100. Okay, now now that we know we have done the trend splitting, we need to scale the variable for better interpretability. Okay, but we only need to scale the numeric column, not the dummy variable. So let's take a look at the list of numerical variable we have created in the beginning. Also, the scaling has to be done only on the training data set, as you don't want it to learn anything from test data set. Okay, so let's see what all features. Okay, car numeric dot columns. So let's scale all these column with standard scaler. You can use any other scaling method as well, it is totally up to you. So also note that you have converted two other variable, that is door number and cylinder number, to numeric type, so we need to include them in the var list as well. Okay, so let's import the standard scaler. So from Scikit-learn dot preprocessing, import standard scaler. Okay, now let's create the scalar object. Okay, so scalar equal to standard scalar. Okay, now create the var list. And here it will include all of this feature. Okay, symboling is there: wheelbase, car length, car width, weight, engine size. Is engine size? Yep. Okay, then we have bore ratio. Okay, I think we do not have door number and cylinder number, so let's include them. Door number, cylinder number. Okay, now we need to scale this variable using fit transform. So how to do that? So tf train, oops, not this, if train of our variable list, okay, is equal to scalar dot fit transform df train of var list. Okay, so let's run it. So it says df okay, so it is df train. Okay, so we have scaled our features. Now let's see how they look like. Okay, how to see that? With head function. Okay, so now you can see that most of all the numeric features came down in between -1 to 1. Okay, now what we need to do is we need to split the data set into x and y. Okay, so for that, y train will be df train dot pop price. Okay, now x train will be df train. Okay, so now we have y train and x train. Now let's build the first model with all the features. Okay, so what we need to do is we need to import, so let's say we are doing linear regression, so for that let's import the linear regression function. Okay, so how we do it? Let's import it here. So from Scikit-learn dot linear model, okay, import linear regression. Okay, so let's run this. Now let's build the model. So let's instantiate, so this is lm equal to linear regression. Okay, now let's fit the line. So lm dot fit x train and our y train. Okay, now we have trained our linear regression. Now let's print the intercept and coefficient. So how we do it? Print lm dot coef as well as print lm dot intercept. Okay, so now we'll see all of our coefficient and intercept. Okay, so we can see our intercept is 97. So the model, let's do now our model using RFE. Okay, So basically now we have close to 60 features, so it is obviously not possible to eliminate these features. So let's now build a model with recursive feature elimination to select features, and we will start off with an arbitrary number of features, and 15 seems to be a good number to start with. And then we will use stats model library to build the model using shortlisted feature, and this is also because Scikit-learn don't have adjusted R square that stats model has. Okay, and for that reason let's do it. So let's import RFE. So from Scikit-learn dot feature selection import RFE. So let's do RFE with 15 feature first. Okay, now RFE1 equal to RFE our model, and we need to pass how many feature we want, 15. Okay, now let's fit the model. Okay, so RFE1 dot fit x train comma y train. Now let's print support and ranking. Okay, and it will be a boolean result. So let's do that. RFE1 dot support and our ranking. Okay, so it says RFE take 2 argument, but we have passed 3 argument. Okay, so I think it need to be passed as a parameter name. So the name of the parameter is, to check, since I don't remember, to check you can click shift tab and you will be given the simple implementation of this particular function, and what we are looking for is n feature to select. Okay, and you will find all the docstring, name of the parameter, what it does, all of those things. Okay, just remember shift tab. So let's copy this parameter name and make it equal to 15. Now you can see that we have got the output. So wherever it find it is important, it has marked as true. Wherever it is didn't find important, it is marked as false. Okay, and ranking as per how they I mean what is the rank actually they have got. So now let's see by evaluating the particular model. Okay, and for that we need to import the stats model library. Okay, so for that let's import that. Import stats model dot API as sm. So now let's create a variable where we will be subsetting the feature selected by RFE1. Okay, so xtrain dot columns, here we will pass RFE1 dot support. Okay, now subsetting the training data for 15 selected column. So xtrain underscore RFE1 equal to xtrain of col1. Now we will add a constant to the model. Xtrain RFE1 equal to sm dot add constant xtrain RFE1. Okay, now let's see how they look like. Okay, now you will see we have a constant and all other feature value. Okay, all those selected. Now let's fit the model with 15 variable in the least square method. Then we will get our adjusted R square value. Okay, so let's fitting the model with 15 variables, and it will be lm1 equal to stats model dot ols, and here we will pass y train. Okay, and then our 15 feature x train. Okay, and then we'll fit, and let's print the summary. Okay, so lm1 dot summary will give us summary. So let's run this. Now it is running and showing some error. So it says pandas data cast to numpy data type of object. Okay, where the error is coming? Okay, here only. Okay, it's fit, not fit. Okay, so sorry. So what mistake that we have done is we have forgot to convert this boolean value to 0 and 1, and because of that this error is coming. So what we need to do is let's come here where we created our x train and y train. So here we will add one more line, that is x train of I lock all rows and from 1 2 3 4 6 7 8 17th. Okay, from 17th onward, what we want to do, we want to convert all the boolean to 0 or 1. Okay, so for that, x train dot I lock all rows 17th onward, we need to make as integer value. Okay, so as type int will make true as 1, false as 0. So let's run this code, and what we will see that it has been converted to 0 and 1. So let's see our head. Now you will see the rest of all the values same, only after 17th column, that is after price. Okay, there's still a few which has been left as it is. Okay, so let's fix this as well. So it should be 16th onward, because we have dropped price from the the white train, so that's why. Okay, so let's do that again. Okay, so our x train is modified, so let's fix that issue first, and now let's run this again, and now you can see that it has been correctly converted to 0 and 1. Now let's train our linear regression model again. Okay, let's fit our intercept again, all of this step. Now I don't think this error will come. Yeah, so we can see that the error that has been rectified. Now what we see here is that the model seems to be doing good. You can see that our R squared value is around 90 2%, and adjusted R square is 91%. Okay, so you can see that most of the p value is less than 0.05, which means they are making sense. Okay, so let's what next we can do is let's check VIF value for these features. So for that, let's import VIF. Okay, so from stats model dot stats dot outliers influence, import variance inflation factor. Okay, now let's create a data frame, VIF equal to pd dot data frame, and VIF dot features xtrain RFE dot columns. Okay, now VIF of VIF feature will contain the values, and here we will use a list comprehension method to do that. So here we will pass our xtrain RFE dot values I for I in range of xtrain RFE dot shape of 1. Okay, VIF round of VF2. Now let's sort it in a descending order. So VIF equal to VIF dot sort sort values, and it should be by equal to VIF value, and then ascending equal to false. And let's see our VIF. You can see that there are few variable with infinite VIF, so this variable are not of use, but manually elimination is time consuming and make the code unnecessarily long. So let's try to build model with 10 feature, this time with RFE, and see what we get. Okay, so let's copy the same code that we have used above for 15 features with 10 features. Okay, so we have selected 10 features. Let's run this. Okay, now what we need to do is same theme again, we'll add constant and we'll train a OLS. Okay, So just copy, sorry for that. So let's copy the code from here to here. Okay, so we have taken all the 10 features, and let's rename it to column 2. It should be RFE2, and this one should be RFE2. Let's make this RFE2 as well. Okay, okay, so now again we have trained our model. Now you can note that the R squared value hasn't dropped much practically, so it has gone from 91 to 90 901. So 10 variables seems to be a good number to start with. Okay, so now again check the VIF. Okay, so let's copy this line of code. Okay, now let's change all of the variables. Yeah, now we are good. Okay, so there are still some variable that need to be dropped, so let's start by dropping car company, Subaru. Okay, so we will do refitting the model with 9 variable. Okay, and this is how you do iteration in every model. You will take certain number of feature, you will train again, you will take certain number of feature and train again, drop, train again, drop. So this is how whole iteration works. Okay, okay, so refitting the model with 9 features. Okay, so we do not see any improvement, but let's see the VIF score. Now you can see that the infinite VIF has now dropped to be a workable value, but from p-value perspective, the engine OHFC has become insignificant. So let's drop that as well. Okay, and we'll train the model again. Okay, let's drop that, and let's train the model again. Let's see. Okay, we haven't trained, so let's paste that. So the variable seems significant, but we still have high VIF. So let's drop them and see if adjusted R square is getting affected or not. So what we can drop is this car company Peugeot. We can drop this and we can train the model again. So let's drop this, train the model again, and we'll recalculate the VIF. Okay, so let's copy that and paste it again. Okay, so we will drop this feature. So after dropping that features, let's train the model again. Okay, then let's run the VIF again. Okay, so we can see now the engine type L variable now has p value of 0.3. So let's drop it and see if it affect the model much. Okay, so okay, so R square has been dropped to 89. Let's see the VIF. Okay, so all the VIF value and p value seems to be in good range. Okay, and also the R squared value has dropped from 0.91% with 15 variable to 89% with 6 variables. So the model is explaining most of the variance without being too complex. So let's proceed with this model. Now let's do the residual analysis, which is error analysis. Okay, so before we make prediction on test data, let's first analyze the error, and that is what meaning of this residual analysis is. So y train price equal to lm2 dot predict x train rfe2. Okay, so let's plot the histogram of error terms. To plt dot figure, then we have sns dot displot y train minus y train price. Let's define the bin size also. So bins, I want it to be 25. Okay, so fig dot subplot, subtitle error terms, then we'll have font size equal to 20. Let's plot the x label also. Should be errors, then font size, let's make it 18. Okay, let's plot it. Okay, we have some error text. Okay, so the error term are fairly normally distributed. As you can see, the curve is like normal, bell shaped, and we can surely live with this. Let's now make the prediction on test set. Okay, so this all thing you will be doing in the real project also, same way. So now df test, the variable list, you remember, right? So scalar dot transform df test with var list. Okay, it was underscore. Yep. So now we'll split the df test into x and y. Okay, so y test equal to df test dot pop the price. Okay, x test equal to df test. Okay, now let's see what is all inside call to. Okay, we have all these features, so let's subset these column to and create a new feature called x test rfe2. So for that, x test rfe2 equal to x test rfe2 dot drop engine type OHFC, which we have dropped in xtrain. Okay, then we dropped this particular car company. Okay, then we have dropped engine type L as well as car company Subaru. Okay, so since we have dropped this feature from train, we need to drop from test also. So now axis will be 1. Okay, it says not defined. Okay, why it is not defined? Oh yeah, okay. X test of call to. Okay, so we have dropped now. Now let's add a constant. So x test rfe2 equal to sum dot add constant x test rfe2. Let's see the information about this data frame. So we have float and boolean values. So again, you remember why there was some error coming because of boolean value, so we need to fix that boolean value, right? And so is to 16. Where is that? Okay, this particular line we have to do it for test data set also. So now how many columns? 1 2 3 just after 3. Okay, 3 3. Now you can see that it has been successfully converted to the numbers. I have just one question here. Dot head. Okay, yeah, so let's drop it now. Since we have converted into correct value, now let's do the prediction. So making prediction here. Okay, so y pred equal to model2 dot predict our x test. Okay, or if it 2. So we have done the prediction. Now let's plot the graph. So we'll plot y test and y pred to understand the spread of data. Okay, so fig equal to, let's take a default figure. Okay, so let's plot this. So what we observe is that from the above plot, it is evident that the model is doing well on the test data as well. So let's also look the R squared, and more importantly the adjusted R square value for the test data. Okay, so for that we need to import the matrix. Okay, from Scikit-learn dot matrix, import R2 score y test comma y prediction. Okay, this is capital. Yeah, so what we are we are getting here is that for the model with 6 variable, the R squared on the training and the test data is about 90%. Okay, so the adjusted R square on train set was about 89%, right? So it is evident that the model is doing same. I mean the performance is in test and train accuracy is almost same. So we can say that the model is good as very good model. So that is what we can convey with this type of performance. So now what we can do is, let's plot the heat map and we'll see how they look like. Okay, so call to drop. So we'll drop some features here, that is okay, this feature only. So let's copy this. Okay, now let's plot it. So plt.fig fig size equal to 8,5. Now heat map sms dot map cards of call to yellow, green and blue. Okay, and will not equal to true. Now let's plot it. Okay, so though this is the most simple model we have built till now, few final prediction still seems to have high correlation. Okay, so one can go ahead and remove some of this feature through that will be affected with adjusted R square significantly. So you should try doing that. Thus for now the final model consists of 6 variable mentioned above. So hope you guys have learned so many things here in this project, and hope you will be implementing such detailed level of iteration step, because this is what I actually do when I am working with a real-time project. I mean, the cleaning part and the data quality part didn't have much in this data set, so whatever needed we have done, but in real case scenario there will be many more thing to do. So I mean, moving forward we will be learning all those things as well, since I will be covering every single aspect in the machine learning, so don't worry about that. Also about this notebook, I'll be adding link to the GitHub, so you can download this notebook from there and you can do more practice on this, as well as include so we were having around 60 features, so we have trained the model on 15, and moving forward 10, 8, 7 like that, okay, and finally 6. So you can start with top 50 feature and then start reducing to 40, 30 like this, and then you can see the variability in the model, and you will be able to see how reducing feature or increasing feature affect the model. Okay, so thank you so much guys, see you in the next video.